So, I mean, this is really the punchline, is that this line holds if and only if e after the name of gamma, comma x equals fx, because this line holds if and only if this after name of gamma equals this after name of gamma, okay, which gives us this line. And then it turns out that this left-hand side here, e after the name of gamma, comma x, just simplifies to gamma x. So I'll show you a little proof of that in a minute, but notice how this substantiates our claim, because we essentially have that the name of gamma is in this extension here. Well, I could say this extension here, it's the same, okay, if and only if gamma after x equals fx, okay, which is what we wanted. Now, why is this equivalent to this? Well, it can basically be seen from this diagram here, okay, because this is the top line, because this line here is essentially e after the name of gamma, comma x, composing along these green arrows, whereas composing along these purple arrows at the bottom just gives us gamma after x, and we see that this diagram commutes, which completes the proof. So okay, that's nice. Now let's do something more ambitious. Okay, so one thing that it was a problem that I came across when I was researching something else, but it's an interesting problem in general, which is, let's say you have a subobject, say S star. Okay, so this next thing I want to talk about, this is a problem which arose for me during researching some other topic, but it seems like an interesting problem, and it's very apt for sort of using this kind of Mitchell-Benebow notation. So the problem is we have some subobject x. So the problem is we have some subobject s of our object capital X, and what we want to do is to describe the collection of subobjects which contain S. Okay, so this is again a problem of a kind of higher level to anything we've thought about so far, because we really want to get a whole collection of all of the kind of subobjects that contain S. So the solution to this is not going to be a kind of ordinary subobject of an ordinary object. It's going to be a subobject of omega to the power x, okay, because it's going to be a sort of, we're going to be representing it as a collection. I mean, if we're thinking of it in set theory, we'd be thinking of it as a collection of the maps from X to omega, okay? But I mean, we like to describe everything internally in general toposes, so for us, it's going to be a subobject of omega to the power of X. And essentially, we want this so that if we have a point of this subobject, say name of alpha is our point, then we want it to be such that we want this subobject to be such that the name of alpha is going to be in this subobject if and only if S is contained in the subobject classified by alpha. Okay, so let's see if this works. So, okay, let's see if we can do this then. So here's my proposed description of this subobject. I say it is the extension of for all x, chi s x implies x in n. I claim it's the extension of for all x, chi sx implies x in n, where we're doing the extension over all n, which are variables of omega to the power of x. So, firstly, how did I come up with this formula? Well, the truth is, it was by quite some experimentation and working from both sides, but ultimately you can think of this as kind of inspired by how you would describe this kind of problem in set theory. Okay, so in set theory, you'd be saying something like, well, I want to have some kind of a collection of subsets n which have the property that for any x, we have that if x is in S, as in if chi s x is true, then we should have that x is in n. Okay, so if I can find all of the kind of subobjects with that property, that, you know, whenever we have an element little x of capital X, we have that if little x is in S, then little x is in n. So, like in set theory, I'd want to sort of find the collection of subsets n of capital X such that if an element little x is in S, then the little element x is in n. Okay. So that's kind of what I want, and you see what I've written here is basically that. Okay, because saying chi s x is true is like saying that x is in S, and whenever that happens, we want x to be in n. Now, it's a bit funny because what I've done here is use some of these kind of abbreviation. Now, it's a bit funny because what I've done here is use some of this kind of abbreviation notation. For example, when I write x in n, that's, as I said earlier, just sort of abbreviation for really saying en comma x. Okay, so it takes a bit of work to prove this, but it's interesting because we're going to be applying lots of the things that we've been learning about in order to prove this. And if you know all the results, it's quite mechanical. We just sort of keep thinking of ways to do substitutions until we're done. So let's do this proof. So let's go then. We suppose that we have this point name of alpha of omega to the power of x, and let's suppose that it's in our extension here. Well, another way we could say this is that the name of alpha is in the subobject classified by for all x chi s after x implies. So another way we can say this is that name of alpha is in the extension of the interpretation of for all x chi s x implies x in n. And then if we work out this interpretation, we can rewrite this as saying name of alpha is in for all subscript capital X transpose of the interpretation of chi s x implies x in n over n and x. And then we want the subobject classified by that. Okay. And another way we can say that is to use our sort of result about universal quantification. So again, you might want to look up the universal quantification proof for more kind of background on this, but we can rewrite this as a name of x is in for all little x, interpretation of chi s x implies x in n over n and x, and we want the subobject classified by that. So this is going to be a subobject of omega to the power of x times x now. And then we can use the theorem proved in the video universal quantification proof, as we've discussed before in this Mitchell-Benabal language video. So we can rewrite this as saying name of alpha times identity is in chi sx implies x in n. Well, we want the interpretation of that over n and x, and then we want the subobject classified by that. And then, of course, we're using this x in n notation here. So let's write out what that means, because this is just abbreviation. So we can replace that with en comma x. And then we just want to sort of compute this interpretation here. And so we do that on this line. So the interpretation of this is implies chi s p2 comma e. And so we're saying that, basically saying that name of alpha is in our original extension is equivalent to saying that name of alpha times identity is in the subobject classified by implies chi s p2 comma e. And then we can just say, well, let's take the classifying arrow of this subobject, as in let's take the stuff inside the brackets, and we're going to have that this holds if and only if doing such an arrow after the name of alpha times identity of x sends everything to true. So we have that this stuff holds if and only if implies chi s p2 comma e after name of e P1, P2 sends everything to true. And the reason I write this is because this is just the sort of expanded out version of what name of alpha times identity x is. It's just this if we want to use sort of pure angle bracket notation. And then we can just calculate what this left-hand side is. And we find that it's equal to implies chi-s p2 comma alpha after p2. And now we can use one of our previous results that says that when we have something implies something, sends everything to true, that's equivalent to saying that the subobject classified by the first something is contained in the subobject classified by the second something. So this is equivalent to saying that chi-s after p2, so this is equivalent to saying that the subobject classified by chi-s after p2 is contained in the subobject classified by alpha after p2. And now another result, which we've already kind of come across, is that we have that the subobject classified by chi-s after p2 is equal to the pullback of s along p2. Okay, so using this kind of idea, we can say that this holds if and only if the pullback of s along p2 is contained in the pullback of alpha star along p2. And now there's a sort of big jump in logic, which is that this happens if and only if s is contained in alpha star. And so I'll prove this last step in a minute because it's quite involved. But just notice we've basically completed the proof now, because we started by assuming that the name of alpha is in this extension, and we've shown that that's equivalent to saying that s is contained in alpha star. And that's just kind of what we wanted. But we still need to prove this last step. So I've got two sort of lemmas which I use to prove this. So the first lemma is kind of universally useful. It's just an alternative way to think about the pullback of a subobject along one of these projections. So an alternative way to think about this, for example. And what it says is that the pullback of s along p2 is equal to the identity arrow of omega to the power of x times s. And the way we prove this is we consider a general kind of arrow into omega to the power of x times x, and we're going to show that that's going to be in identity times s if and only if it's in the pullback of s along p2. Okay, so let's do this. So suppose that L1 comma L2 is in identity times s. Well, that holds if and only if there exists K1 comma K2 such that L1 comma L2 is equal to identity times S after K1, K2. And writing this identity times S in angle bracket notation and kind of calculating out what this composition is, we find that using K1 equals L1 always satisfies this. So basically, this condition holds if and only if there exists a K2 such that L2 equals S after K2. And that clearly holds if and only if doing P2 after L1, L2 is going to be in S. And one of our previous results about inverse images then tells us immediately that this happens if and only if L1, L2 is in the pullback of S along P2. So that completes our proof of lemma 1, because we've essentially shown that this general arrow is in identity times S, if and only if it's in the pullback of S along P2. Now we get on, so this is a lemma which is kind of useful in general, and notice that there's some kind of interesting connections between this and the idea of sort of doing extensions over formulas where you're including kind of redundant variables. Because if you just do an extension where you only use precisely the free variables in your formula, you get one thing, let's say S, but if you then say add an extra variable, you'll get something like P2 to the minus 1 of S as your subobject classified. And this really characterizes such a thing. And also there's some connections between this and ideas of for all, as we shall see shortly. But the next, well, as we're seeing at the moment, really, but the next result then is actually finishing our proof, because it's proving that this line here is equivalent to this line here. And that's pretty much exactly what our next lemma states. So our statement then is that the pullback of S along P2 is contained in the pullback of alpha star along P2 if and only if S is contained in alpha star. So the hard part first then is to prove that the left-hand side implies the right-hand side. So we'll suppose the left-hand side, suppose the pullback of S along P2 is contained in the pullback of alpha star along P2. And then we want to show that S is contained in alpha star. So we're going to suppose we have a general kind of arrow L2 in S. And then we want to show that that L2 is also in alpha star, and that'll prove the right-hand side. So suppose L2 is in S. Well, then that obviously means that there exists a K2 such that L2 equals S after K2. And so we have a kind of triangle like this. And now what we want, for reasons that will soon become apparent, is we want some arrow from L to omega to the power of x. Now, we don't really care what that arrow is, but here's a way we can get an arrow like that. We can consider true after exclamation mark L times omega. And that's obviously going to be an arrow from L times x to... Whoops. So, as I was saying, we basically just want any arrow from L to omega to the power of x. And so a way we can make such an arrow is we can consider true after exclamation mark L times x. And then if we just take the transpose of that, that will be an arrow from L to omega to the power of x. And I may just refer to this arrow here as Z, just for short. Okay? Because it doesn't really matter what it is, actually. Just the fact that we have an arrow from L to omega to the power of x will suffice for our argument. Okay, so the next claim then is, I mean, we know that this triangle commutes. The next claim is that this triangle commutes. So basically we have Z comma L2 is equal to identity times S after Z comma P2. Okay. And here's the proof that that works out. So the point really is that we have Z comma L2 is in identity times S. And we know identity times S is the pullback of S along P2. And so since we're assuming that the pullback of S along P2 is contained in the pullback of alpha star along P2, you know, we said up here, then it must be that Z comma L2 is in the pullback of alpha star along P2. But then that means that P2 after Z comma L2 should be in alpha star by the sort of how the inverse image works in terms of elements. And we know that P2 after this is just L2. So we've finally got that L2 is in alpha star. So to conclude, we assumed this, we assumed L2 was in S and we got L2 is in alpha star. So we've proved that the left-hand side implies the right-hand side. Now we just go the other way around. That's much easier. So let's suppose that S is contained in alpha star. So let's suppose that S is contained in alpha star. And now we're going to suppose we've got a general element L1, L2 of the pullback of S along P2. Well, that means that P2 after L1, L2 is going to be in S, which means that P2 after L1, L2 is in alpha star, which means that L1, L2 is in the pullback of alpha star along P2. And so again, we've got, if we assume we have an element of pullback of S along P2, then we get that that's actually also an element of the pullback of alpha star along P2. Hence, the pullback of S along P2 is contained in the pullback of alpha star along P2. So we've got the other way around now. We've got that the right-hand side implies the left-hand side too. So that proves lemma 2, and that proves the last line of this, and that's it. That's what we wanted to show. So it's quite remarkable that just by sort of thinking about how we'd say something in terms of set theory, writing it down in a Mitchell-Benebao language, and writing it down in Mitchell-Benebao language, we can really get the kind of formula that we're after, and then we can prove it using a relatively small number of these kind of topos theory kind of identities. So yeah, there we go.